Have you ever stopped to think about the material that builds our modern world? Look around you. The towering skyscrapers that define our cities. The cars and trains that carry us from place to place. The bridges that span vast rivers. Even the simple fork you use for dinner. At the heart of all these incredible achievements lies a single, powerful material: steel. It is the silent, unsung hero of our civilization. Steel is not just one material but a family of materials, combining iron with a small amount of carbon. The true genius of steel lies in its incredible versatility. Engineers and scientists have learned how to tweak this basic recipe, adding different ingredients to create specialized types of steel. In this exploration, we will focus on two of the most important members of the steel family: alloy steel and carbon steel. While they both share a common ancestry, their paths diverge significantly, serving very different purposes in industry. By the end of our journey, you will understand what makes them different. Let's begin our story of steel. Imagine you are a chef. Basic steel is like a plain dough, strong but limited. Alloy steel starts with basic steel but incorporates other elements to create extraordinary new properties. Alloy steel is the material of choice when the job is tough. Alloying elements can give the steel incredible resistance to rust, make it hard enough to cut through other metals, and withstand extreme temperatures, a necessity for jet engines. On the other side, we have carbon steel. Carbon steel is the reliable, everyday bread and butter. Its primary ingredients are simply iron and carbon. Because it is easier and cheaper to produce, carbon steel is the most widely used type of steel. It is found in everything from the structural beams of your house to the body panels of a family car. So, when do you need alloy steel? And when is carbon steel the right choice? Understanding the trade-offs between performance and cost is a fundamental skill. What makes an alloy steel special? It comes down to the ingredients, like a secret recipe. The base is iron and carbon, but the magic happens when we add a carefully measured mix of alloying elements. These elements unlock steel's hidden potential. Chromium adds a protective shield, increasing resistance to rust. Nickel adds toughness and resilience. Molybdenum improves strength and hardness. Vanadium increases toughness and wear resistance. The beauty lies in the synergy of these elements. Metallurgists fine-tune the steel's properties, creating a custom material for specific problems. Creating alloy steel involves intense heat, precise control, and a dramatic transformation of raw materials. The journey begins with a massive furnace, either a traditional blast furnace or a modern electric arc furnace that melts down scrap steel. The result is a cauldron of molten steel. Alloying elements like chromium, nickel, or manganese are added in precise amounts. The mixture is stirred, creating a homogeneous liquid alloy. The molten alloy steel is then cast into molds to cool and solidify into slabs, billets, or ingots. These are shaped through rolling or forging. Rolling squeezes the steel into sheets, bars, or beams. Forging hammers the hot steel into specific shapes, refining its grain structure for strength and durability. After alloy steel has been cast, the most crucial step is heat treatment. It's a controlled process of heating and cooling to manipulate its internal crystalline structure or microstructure. By changing this structure, we can alter the steel's mechanical properties. One common process is annealing, like a reset button. The steel is heated and then cooled slowly, relieving internal stresses and softening the metal. On the opposite end is quenching, creating extreme hardness. The steel is heated to a high temperature and then cooled rapidly. This freezes the steel's internal structure in a hard, brittle state. Tempering gently reheats this hardened steel, relieving some internal stress. This trades a small amount of hardness for a significant increase in toughness. This three-step dance transforms metal into a precisely engineered material. Let's delve into the real world, where alloy steel proves its worth every single day. One of the most demanding environments is inside the engine of your car. Critical parts like the crankshaft are forged from high-strength alloy steels, giving them the muscle to handle immense forces. The same principles apply to other key parts of a vehicle's powertrain and chassis. Similarly, axles and suspension components are made from tough, durable alloy steels. Now let's take to the skies. The aerospace industry pushes the boundaries of material science further than almost any other field. They are used to manufacture some of the most critical components of an airplane, such as the landing gear. The turbine blades and discs at the heart of the engine are crafted from sophisticated nickel-based or cobalt-based superalloys. Without these remarkable alloy steels, the power, efficiency, and safety of modern air travel would simply not be possible. Powering our world demands materials that can withstand extreme environments, deep-sea oil rigs, power plants, and more. Alloy steel is the backbone here, used in drill bits, pipelines, boilers, and turbines, all engineered to resist corrosion and endure high pressures and temperatures. Chrome moly steels in particular keep power plants running safely and efficiently. Now zoom in to the tools that shape our world. Cutting, drilling, and machining tools all rely on tool steels, a special class of highly alloyed steels. High-speed steel with tungsten, molybdenum, and vanadium stays sharp and hard even under intense heat, enabling fast, precise manufacturing. From woodworkers' chisels to massive stamping dies, alloy steels ensure tools withstand repeated impacts and wear. Different alloy combinations create tool steels for specific needs: shock resistance for jackhammer bits, extreme wear, resistance for injection molds. Without these tough alloy steel tools, mass production would be slow, inefficient, and costly. Alloy steels are the unsung heroes powering industries and building the tools that build our world. Their reliability and strength keep our modern lives running smoothly. Modern suspension bridges with their soaring cables showcase alloy steel's strength on a grand scale. High-strength alloy steel wires bear immense loads, enabling lighter, longer, and more elegant structures. In earthquake-prone zones, alloy steel rebar reinforces skyscrapers, adding crucial safety and flexibility. Corrosion-resistant alloys protect marine structures from relentless saltwater, ensuring longevity. In medicine, stainless steel, an alloy with chromium, makes surgical tools that resist corrosion and hold sharp edges for precise operations. Implants like hip and knee joints use biocompatible alloy steels, designed to be strong, non-toxic, and durable inside the body. These materials must endure years of stress and wear, restoring mobility and improving lives. From monumental bridges to life-saving surgery, alloy steel is essential to progress and well-being. Its versatility bridges the gap between strength and precision. Alloy steel shapes both our world and our health. Now let's shift focus to carbon steel, the workhorse of the modern world. Unlike alloy steel's complex mix, carbon steel is defined by just two elements, iron and carbon. Its simplicity makes it affordable, strong, and easy to produce on a massive scale. Carbon steel forms the backbone of infrastructure, vehicles, and appliances worldwide. The key is carbon. It hardens steel by distorting the iron's atomic grid, making it stronger as more carbon is added. This direct relationship explains why carbon steel is so versatile. From soft wire to hard-cutting blades, adjusting carbon content tailors its properties for countless uses. Carbon steel's straightforward chemistry is its greatest strength. It's the reliable foundation for building, manufacturing, and everyday life. Simple, strong, and indispensable. Carbon steel comes in three main types, defined by carbon content: low, medium, and high. Low carbon steel, up to 0.3% carbon, is soft, ductile, and easy to form, ideal for car bodies and appliances. Medium carbon steel, 0.30.6% carbon, is stronger and harder, perfect for machinery parts, axles, and railway tracks. High carbon steel, over 0.6% carbon, is the hardest and most wear-resistant, used for cutting tools, springs, and high-strength wires. As carbon increases, steel becomes harder, but less ductile and more brittle. Each type serves a specific purpose: low carbon for easy fabrication, medium carbon for balanced strength, high carbon for extreme hardness. Engineers choose the right carbon steel based on the demands of the job. Adjusting carbon content unlocks a spectrum of properties from just iron and carbon. This versatility makes carbon steel a fundamental material in engineering. The right carbon level means the right tool for every task. Simple adjustments, endless possibilities. That's the power of carbon steel. Making carbon steel starts with molten iron, produced in blast or electric arc furnaces. The molten iron, rich in carbon, is refined to remove excess carbon and impurities. In a basic oxygen furnace, pure oxygen burns off unwanted carbon, precisely controlling the final content. Unlike alloy steel, carbon steel production focuses on subtraction and purification, not adding expensive elements. Once refined, the liquid steel is cast into shapes: slabs, billets, or blooms. These are rolled into final products: beams, sheets, rails, and bars. The process is efficient, cost-effective, and scalable for global demand. Simplicity in chemistry makes carbon steel production straightforward and affordable. This streamlined process delivers the world's most essential engineering material. From furnace to finished product, carbon steel is made for mass production. Its journey is as practical as its uses. That's why carbon steel is everywhere. Look around, carbon steel is everywhere, forming the backbone of cities and infrastructure. Skyscrapers rise on carbon steel I-beams and columns, chosen for strength, cost, and ease of construction. Pipelines carrying water and gas, bridge girders and trusses all rely on carbon steel's durability and affordability. Reinforced concrete uses low-carbon steel rebar, giving buildings the strength to last. Construction equipment, dump trucks, bulldozers, excavators, depend on tough carbon steel for daily heavy-duty work. Carbon steel's strength and practicality make modern construction possible on a massive scale. From foundations to rooftops, carbon steel is the silent partner in building our world. Its reliability shapes the cities and infrastructure we depend on, strong, affordable, and everywhere. Carbon steel is the backbone of progress. Now let's bring it closer to home and look at the objects we interact with every single day. The automotive industry is one of the largest consumers of carbon steel, particularly low-carbon steel. The body of the car you drive, the doors, the roof, the hood, and the fenders, is made from large sheets of this material. Why? Because low-carbon steel is highly formable, allowing manufacturers to press it into complex and aerodynamic shapes. It also provides a crucial safety cage that crumples in a controlled way during an impact, absorbing energy and protecting passengers inside. It delivers this life-saving performance at a cost that keeps cars affordable for millions. The world of transportation runs on carbon steel. Consider the shipping industry. The enormous hulls of cargo ships, the supertankers that carry oil across oceans, and the humble barges that move goods along rivers are all constructed from massive plates of carbon steel. It provides structural strength to withstand the powerful forces of the sea and the immense weight of cargo. Its weldability allows shipbuilders to join these huge plates together to form watertight and robust vessels. This makes global trade and movement of goods economically possible, connecting economies and stocking store shelves. Let's step inside your home, into your kitchen. Many everyday items you use are products of carbon steel. That sturdy frying pan or wok that heats up quickly and evenly is likely made from carbon steel. The bodies of your refrigerator, washing machine, and dishwasher are formed from sheets of low-carbon steel. Even smaller items like nails, screws, and bolts that hold your furniture together are mass-produced from carbon steel wire. Its combination of strength, low cost, and manufacturability makes it ideal for a vast array of consumer goods. This widespread use shows carbon steel's incredible versatility and economic efficiency. Manufacturers choose it because it gets the job done reliably without adding unnecessary expense. For products produced by the millions, from paper clips to car frames, this cost consideration is paramount. It allows companies to deliver functional, durable products to mass markets. While it may not have the glamour of high-tech alloys, carbon steel is the quiet enabler of our modern consumer lifestyle, present in countless objects that make our lives easier, safer, and more convenient without us ever giving it a second thought. While alloy steels are known for high performance, carbon steel has its niche. High carbon steel is heat-treated for hardness. It's fantastic for hand tools like hammers and axes. Many chefs prefer high carbon steel knives. Wrenches, screwdrivers, and pliers are often made from medium or high carbon steel. Carbon steel components are common in industrial machinery. High carbon steel is iconic for springs. From small springs to vehicle suspensions, it provides tensile strength and elasticity, storing mechanical energy. Alloy steel and carbon steel differ significantly in performance. Alloy steels excel in strength and hardness, especially at high temperatures, due to elements like tungsten and molybdenum. They also offer superior toughness, absorbing more energy without fracturing. Corrosion resistance is another key advantage. Carbon steel rusts easily, while alloy steels, like stainless steel with chromium, resist corrosion. Alloy steels also demonstrate better wear resistance and fatigue strength. Elements like chromium and vanadium create hard carbide particles, protecting against abrasion and resisting cracks under repeated stress. Performance is only half of the story. Cost and manufacturing are just as important. Carbon steel is dramatically favored here due to raw material cost. Carbon steel is made from iron and carbon, two of the most abundant and inexpensive elements. Alloy steels require additions of costly elements like nickel, chromium, and molybdenum, which fluctuate significantly on the world market. This cost disparity extends into manufacturing. Producing carbon steel is straightforward. Alloy steel making is more complex, requiring precise amounts of expensive alloying elements. This brings us to machinability and workability. Low-carbon steels are easy to cut, drill, bend, and stamp. Alloy steels designed for hardness and strength are inherently more difficult to work with. Heat treatment also adds to the complexity and cost of using alloy steels. The decision often comes down to a simple question: is the superior performance of alloy steel worth the significant increase in cost? How does an engineer make the final call between alloy steel and carbon steel? It's a balancing act between performance and cost. Consider the environment and stresses. High temperatures, corrosive chemicals, high impact loads. Alloy steel is designed for harsh conditions where carbon steel would fail. For less demanding applications, carbon steel is the front runner. Its strength is more than enough for everyday applications like building frames or appliances. The decision can also be a hybrid one, like a car using both materials, each playing to its strengths. Intelligent material use optimizes performance and cost. A good engineer knows how to combine them effectively. Understanding this difference is a powerful tool, enabling you to build smarter, safer, and more efficiently. Our journey through the world of steel has revealed a fascinating tale of two materials, each with its own distinct character and purpose. On one side we have alloy steel, the high-performance specialist. It is a material born of complex chemistry and precise manufacturing, engineered with added elements like chromium, nickel, and molybdenum to conquer extreme challenges. It stands strong against intense heat, resists the relentless attack of corrosion, and endures immense stress and impact. From the heart of a jet engine to the tip of a surgeon's scalpel, alloy steel is the material we trust when performance is paramount and failure is not an option. It represents the cutting edge of material science, pushing the boundaries of what is possible in engineering. On the other side stands carbon steel, the unsung hero and the steadfast workhorse of our civilization. Its strength lies in its simplicity, a straightforward combination of iron and carbon that delivers an unbeatable balance of strength, workability, and cost. It is the backbone of our infrastructure, forming the skeletons of our skyscrapers and the veins of our pipelines. It is the body of our cars and the substance of our daily tools. While it may lack the specialized superpowers of its alloyed cousin, its reliability and economic efficiency have made it the most widely used engineering material on the planet, quietly and effectively building the world we live in and depend on every single day. As future engineers, creators, and problem solvers, understanding the difference between these two steels is more than just academic knowledge. It is a fundamental design principle. The choice is a constant balancing act between the demands of the application and the realities of the budget. Knowing when to invest in the superior performance of an alloy steel and when to leverage the practical economy of carbon steel is the hallmark of intelligent design. This decision influences not just the durability and safety of a product, but also its accessibility and its impact on our world. By mastering these materials, you gain the power to not only build the future, but to build it better, stronger, and smarter.